Hi, and welcome to Physics 2212, Lab 3, Magnetic Field of a Bar Magnet. The purpose of this lab was to measure distance dependence of a magnet's magnetic field, and to visualize the magnetic fields using a visual representation in GlowScript. The other purpose was to compare real and predicted distances using the Biot-Savart law. Main results are that when the magnetic meter is far away from the bar magnet, Bx will approach 0T, and Bx increases as the magnetometer gets closer to the bar magnet. We found that N is equal to negative 2.8438 and mu is equal to 4.57 amps times meter squared. Models and principles are the Biot-Savart law, which is shown here, the dependence distance formula, which is shown here, and the linearization formula, which is shown here. The experiment procedure was to get the magnetometer app and find the chip on the phone. And then we had to line up the phone with north so that Bx is equal to 0. We did this by rotating the phone until it lined with north. We then measured the distance between the chip and bar magnet on axis and perpendicular. The initial conditions was that the phone is now aligned with north, the bar magnet is aligned with the magnetometer, and our systems and surroundings were that the system was the bar magnet and the surroundings was everything else. This shows the data and details. The details were that to find the distance of a bar magnet at varying Bx on axis, graph the values as shown, and graph the values linearly. The left yellow column is the on-axis distance from bar magnet at various magnetic fields. The right yellow column is the values of the magnetic field, and the blue columns are the averages of the distances and magnetic fields. And this equation shows the graph and the slope of the line. And here's the linearization equation down here. Data and details part 2. Find the distance of the bar magnet. One of our details was to find the distance of the bar magnet at varying Bx perpendicular. Find By by the Earth based on the longitude and latitude, and then find Bx, By, and Bz based on the magnetometer. We then could correct By due to the Earth, and we found that Bx is 0 at large distances. And here's all the data down here. Our calculations using the linearization equation shown here, we were able to find N is equal to negative 2.8438. Ln of K is negative 13.905. K is equal to 9.14 e to the negative 7 based on the linear slope of the graph, which was shown here. We then set R equal to 1 meter, and we found that mu is equal to 4.57 amps times meter squared. Our code, so this shows our initial values here of mu 0 over pi over 4 pi, mu hat, mu magnitude, and then we have the dipole function and the scales and distances shown here. Code part 2, this was the code to show 2 arrows drawn on axis, 2 arrows drawn perpendicular, and 1 arrow drawn off axis. And for each arrow, a position, color, and axis are defined. Real life similarities and differences. Similarities is that on-axis vectors point in the direction of mu, and perpendicular vectors point opposite of mu. The differences from real life is that our experimental B net value was 6.4511 e to the negative 5t, while B net theoretical B net was 4.5318 e to the negative t, which is roughly a 70.25% difference. And that's shown here, and the arrows are shown in the picture here. So that leads us to questions. What if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? Our Earth's magnetic field would interfere with the bar magnet's magnetic field. That would skew our results. If you were to stick 2 identical magnets together end to end and run the experiment again, our experiment would differ because the magnetic field magnitude would double, but they'd be going in the same direction. And the conclusion is that bar magnets can be modeled as magnetic dipoles. Magnetic fields increase as you get closer to the magnet. Errors include that the magnetometer was not correctly aligned with north, location of the magnetometer